My talk today is about light and interaction of light and matter. And I think we have seen in the morning how light is a very powerful probe, even in the context of neuroscience, right? To probe with fluorophores how neuronal activity works. The problem is that sometimes the interaction of light and matter is very weak, and we don't interact efficiently with it, right? So in that context, people have used for many decades a particular way to enhance and interact more effectively with light, which is the use of optical cavities. Most of us are familiar with it. The canonical optical cavity is these two mirrors, where when light comes in, it's trapped here in this kind of fabric perot, and if matter is put here, we're going to effectively interact more intensely with this light. I mean, these atoms or molecules here will fill the field trap here in a space and in time. And these are actually the two parameters that govern the properties of a cavity, right? Is what we call the mode volume, or the volume that the light is trapped into, in this case in the micron scale, and the time that these photons live here, which is the inverse of the losses of the quality factor. A good quality factor means long life here, so a long period to interact with matter. A short effective mode volume means trapping of the light there. So if we trap in a space, we concentrate better the energy on the matter, and we make it spend more time, we're going to effectively interact much better. So what we try in optical cavities is to reduce the effective mode volumes. You put more light into the matter and increase the quality factor so that the photons live long. That's all the trick, right? But then, again, this can be improved. People have tried to reduce this effective mode volume by using micro resonators with dielectrics. They put the molecules or the emitters here, and the modes of these fields are smaller than this one here. Even photonic crystals that trap light even to really the diffraction limited in a quantum dot here, for example, with a photonic gap trap here. In this context, I introduce now the work we do with a very special cavity, which is this metal insulator metal that traps light, and at the nanoscale we can put matter here, a molecule here, and thanks to the condensed matter excitations, the electron gas, the so-called plasma oscillation of the electrons, we trap the light there. So we have an incredible ability to reduce and trap light to the nanoscale, but the drawback is we have to pay that metals involve tremendous losses, as we all know, and then these photons don't live too long. So it's a trade-off between how much you trap light to interact more effectively with your molecules or emitters, but these photons don't last too long. That's the problem, right? And in this context of plasmonic cavities, I'm going to use two experimental situations to develop our theoretical approaches. Typically, a top-down approach, a tip of an STM on a metal substrate, they form naturally a metal plasmonic cavity. We put the single molecule here, and we're going to be able to probe with light this, assisted by this cavity, right? There's another chemically based approach, more bottom-up, is a little bit more dirty or realistic, right? Where we put a metal gold surface here, we put a self-assembled monolayer here, and then we deposit a metallic nanoparticle, and then we create a natural plasmonic optical cavity here that is going to be able to probe the molecules there. This approach has been followed by Jeremy Baumberg in Cambridge, for example. We collaborate a lot with them. This approach is essential down in Hefe, right? I will talk a lot about these topics today. So then, in order to approach the interactions of these cavities and the matter we put there, theoretically, there are several approaches, but basically you need a triple methodological approach, right? First, you need a condensed matter description of the cavity. You have metals here, metal particles, and they trap light, and you need to address how this light is trapped, right? There is another ingredient which has to do with whatever we put here, the molecules, the quantum details of the chemistry of these molecules that might be also important. And lately we have exploited a third quantum aspect of these interactions, which is to explore what happens when you quantize the electromagnetic field itself. In second quantization scheme, quantum electrodynamics, what happens when this field is quantized and if nonlinear and coherent effects emerge. So what I'm going to do today is to devote between 5 and 10 minutes to each of the topics and see what we get in digging into this interaction of light and matter. First, the condensed matter approach, right? The cavity, this plasmonic cavity, how it works. We can put a metallic particle close to another metallic particle. We solve Maxwell equations where the light comes in, and we will see how immediately this light is trapped. It's like a squeeze down thanks to these plasma oscillations, thanks to these surface plasmons. You get this by solving Maxwell equations typically, classical approaches, right? But if we zoom here, and we want to zoom here because we're going to probe a few molecules in the nanoscale, we zoom here, and then what we have in this zoom is such a situation, right? This is a metallic tip, for example, a metallic surface and the molecule here. And then in this scale of 5-10 nanometers trapping of light, then the quantum aspects start being important. Classical approaches fail, and what we have done in the group in San Sebastian for the last years is to develop quantum approaches to describe the optical response of this kind of electron gas. You have not any more sharp classical boundaries, but you have a spill out, non-dynamical screening, atomistic effects, and this is something you need to address. I'm not going to talk today about it because it's too much, but we have addressed aspects of non-locality in these plasmonic cavities. We have identified quantum tunneling between two particles at optical frequencies that is expressed in the spectrum, nonlinear response, active control, biasing a cavity and playing with the optical cavity for interconnects, etc., etc. This is a condensed matter approach to see what happens with the photons and the spectroscopy of these cavities, right? So in this context, what we have done very interestingly for optical cavities is a twist of the optical cavity and push this nanoscale optical cavity to the limit. And what is the limit? To do again a zoom here, and in another zoom we go to the atom scale, to the angstrom scale, and we wonder what happens at the atomic scale. And here, classical approaches are not valid, of course. We need a full atomistic description that we do in this situation. The reason why we started paying attention to dimensions smaller than nanoscale and focusing in atoms is again experimental. In this experiment, in tunneling microscopy with the molecule here of Shen Xiaodong, people did laser in, Raman photon out. They described the Raman spectroscopy of this molecule, and this was the result, right? This is a remarkable experiment of this porphyrin-like molecule. You can do Raman, resolve in space at the lobe, at the center. You identify several fingerprints of the molecule. You scan, and you resolve the optical Raman activity of this molecule, resolve within less than 1 nanometer, optically. So this competes with electronic tunneling and local density of states mapping, right? The problem here was that in order to recover and explain the optical resolution below 1 nanometer, in our simulations 4 years ago, we needed to assume a very unrealistic localization of the field. We needed to assume localization of the fields below 1 nanometer. And this was kind of impossible. There's no physical entity that sustained this, right? I have just shown you how here the best plasmonic cavity can control or trap light down to 5-10 nanometers. So what we needed to explain this, at that time we didn't know how to explain it. But then we started describing these cavities in more detail, as I say, paying attention to the atoms. And then with the help of Daniel Sanchez Portal, who is an expert in ab initio in San Sebastian, we were very lucky to be in the same institute. He started playing with these facets, these tips, these edges at the atomic scale and calculating the optical response of these systems. Here I compare what happens when you describe a smooth, even quantum, Gilliam, classical description of the response, this is a plasmon, compare with an atomistic description where you start paying attention to the atoms. This involves non-dynamical screening, spill out, everything. So what is the interesting thing here? On top of this plasmonic localization, a standard localization of fields we have here, in the atomistic description, we see an extra localization here that is trapped right at a single H atom. So one single atom localizes the field, acts as an extreme hotspot, atomic scale optical cavity. Now, if we put our molecule here, this is the most reduced effective mode volume we can have. So now we calculate the effective mode volume. This effective mode volume I have talked before, how much we can trap light to in this kind of cavities. And then we start getting closer and closer closing the cavity down to 1 nanometer, half a nanometer, and we see that for different configurations of the cavity, tip to facet, this one is a tip to facet. There was also facet to facet, tip to tip, but in particular, this is a tip to facet in blue. We get to effective mode volumes below 1 cubic nanometer. So this means that we have achieved a situation in plasmonics where on top of the plasmon background, we put a single atom lighting there, and this can be used as a sub-nano scale optical probe. Okay? The good news is that for experimentalists that are digging or using this kind of string plasmonic cavities, you don't need to do all the quantum calculations to address these features. Quantum calculations are very involved, dynamical screening, many-body. We have just addressed that all these quantum features of description of local fields and trapping have a very classical analog just by purely setting the boundary of the metal following the electronic density of the quantum calculation. So we get exactly the same values of field enhancement, and even with a very rough lining rod effect, which is nothing but this, lining rod effect at the atomic scale, we also get the values and similar distributions of the field. So the good news for experimentalists who want to know how fields localize in single atoms is that we can do a classical calculation taken to the limit in that particular atom or set of atoms, right? So that's for the condensed matter. I have introduced that we have a special cavity that localizes at a single atom an optical probe, right? We have an optical probe. Now let's put matter here and interact with this matter. We're going to interact matter with two types of excitations. One is the vibrations. We have heard in the morning also Raman excitations of the molecule. We put our molecule in the cavity, we come with light in, light out, and we excite vibrations very effectively in the cavity. The other typical canonical excitation is electron-hole pairs, right? We have a molecule in a cavity, we have an HOMO-LUMO transition. This is a fluorescent molecule. If we put this molecule in an optical cavity, this fluorescence will be more effective, okay? So let me dig a little more into that. This is the two-level system. It has a spontaneous decay, gamma, a decay between the excited state and the ground state. We put it in a cavity. The cavity is also a mode, right? It's an optical mode that decays with decay kappa, right? In the case of plasmons, it's very fast decay, femtoseconds or so. And now these two guys interact. And the typical assumption in photonics is that this two-level system transition is a point dipole, that is located in this plasmonic cavity, right? And then when we put this local field of the plasmon cavity acting on this dipolar moment, we can calculate and estimate the interaction between the plasmon and the emitter by just multiplying the field and the dipolar moment integrated and giving this coupling strength, this energy of interaction or energy rate of interaction, right? And now we can distinguish two regimes here in the plasmon emitter coupling. One regime where this coupling energy, this coupling strength is very slow. The coupling rate is very small, and the cavity and the exciton decay faster. So the cavity and the exciton don't have time to interact. Before they start interacting, they already decay. And this is what we call weak coupling. In the energy landscape, the optical mode and the exciton mode will not interact strongly, they will just interfere. And in the dynamics, in time domain, this is what is so-called parcel effect. So the emission of the molecule will be enhanced, or the rate will be enhanced because of the decay into these optical modes. But there is no change of the energy. Now, the other regime of interaction is the strong coupling regime, right? In this strong coupling regime, the interaction between the transition, the molecular transition, and the mode, the optical mode, is very fast. It has a lot of time to interact before they decay, and what it creates is a hybridized situation of modes, two brands, polaritonic brands, where now the molecule in the cavity doesn't have anymore the HOMO-LUMO energy of states of energy that had before. We have reconfigured the energetics of this molecule, and this is very good, for example, for reactivity and so on. Okay? When the molecule has this kind of hybridized situation, in time domain, we can we can address also Rabi oscillations between these two polaritonic branches, right? Let me show you one example of each. We have a plasmonic cavity here, we have a molecule here, and now we can put our plasmonic cavity by moving the tip in these three positions. We have a position very far from the molecule. This is the molecule in topography. The plasmonic cavity is here. There's no interaction. When it's here, it excites the molecule, and when it's here, we just put interaction. So here in green, when we are far away from the molecule, we just have the luminescence of the cavity, the plasmonic cavity. This is the plasmonic cavity, very broad, very lossy. It's just a plasmonic resonator. This is our optical cavity, alone, no interaction with matter. Now we put the cavity with the electrons going and exciting the molecule, and this would be the fluorescence of the molecule, okay? Much thinner, 15 milliV here compared to 100 and something milliV. The interesting thing happens when you put them both relatively close together, in between. And look at what happens. This interaction rate creates this interference between the plasmonic cavity, the optical cavity, and the fluorescence, and creates this funnel-like, this destructive interference of both. And this doesn't change the energetics, but it changes the interference and the spectral features, right? We can actually do the models, see how this interaction is increased as we put the plasmonic cavity closer and closer to the molecule. Is also checked experimentally, right? The limit of this is, it would be a situation where we go into strong coupling. This is a still weak coupling because the dipole of the molecule is aligned in this direction and the plasmonic field is aligned orthogonal. And I have shown you that this interaction energy is the scalar product of dipolar moment and field. So here it's quite orthogonal, and this is why we have weak. But if you manage to align the dipolar moment of the molecule and the local field, you increase the coupling strength, like Jeremy Baumberg did here with this metal in blue in a cage. The dipolar moment is aligned like this, parallel to the field, and then they manage to get a split, Rabi split in frequency and wavelength, and then this is very clearly a fingerprint of a strong coupling. You are modifying the energetic levels of the molecule because they are in a cavity, right? Another interesting aspect of this is what happens when you consider that this dipolar moment is not a point-like object anymore, that you afford and you tackle the full quantum chemistry of this situation. This is very, very important, particularly in plasmonics, not in other optical cavity, but in plasmonics, for example, in this optical plasmonic cavity, when you put a point dipole, if you plot actually the local field associated to these plasmons, for example, in this cavity, you see how the field is extremely inhomogeneous. If this is an inhomogeneous field, a molecule is put there and is considered a point dipole, it's going to be very artificial because the actual molecule might be digging and extending along the whole inhomogeneous field. So what we did now recently is to take one of these plasmonic cavities, put a porphyrin like this zinc PC molecule here, calculate the electronic transition rates, in this case a dipole like this, and then calculate the coupling strength from this ab initio approach with the full transition rate plus the full plasmonic potential. And when you do that, you compare the results of the point dipole in the cavity compared to the full quantum model, and you see that not only the value of the coupling strength, G, changes, but also the symmetries. Here we have a four-fold symmetry that follows the four-fold symmetry of the molecule, and here we have a completely cylindrical symmetry, which is artificial. So considering the quantum chemistry at all levels in the inhomogeneous plasmonic cavity is key to address the value quantitatively and the symmetries of these kind of interactions. Okay? The same happens with the vibrations in Stokes, anti-Stokes, Raman scattering. We have typical Raman scattering of a molecule, here a bipyridine, and we have an experiment of Stokes or anti-Stokes transitions that reveals the fingerprints of these typical three modes. We do the density functional theory, which is the derivative of the polarizability, and we recover the result, right? Bingo, no problem. What happens when you want to enhance this Raman signal, we saw in the morning, and when you put it in this such plasmonic cavity with very homogeneous fields? What happens is that the molecule doesn't feel anymore an homogeneous derivative in space, but it's a very inhomogeneous one. So we have to develop the theory to express all this derivative in terms of atomic coordinates, express this inhomogeneous field acting on each atom to build the vibration, address all of that, and then this is the result. Compared to the plane wave illumination, when we put our molecules in these inhomogeneous plasmonic fields, we get activation of new vibrational fingerprints and what we call breaking of selection rules in Raman. So you have to be, again, very careful what you do with the optical fields acting on the quantum chemistry of these molecules. We can scan this tip, and when we scan on top of the molecule, we'll recover optical Raman tensors below 1 nanometer resolution. So we can finally explain what happened in this experiment and why 4 years ago we artificially had to consider localization of the fields below 1 nanometer. Now we know that in certain configurations of plasmonics with tips and atoms protruding, the fields are localized at 1 or 2 or 3 atoms, allowing the activation of these selection rules of Raman and getting resolution of 1 nanometer. Okay? You don't only need to have this in a top-down STM kind of approach, ultra-high vacuum, low temperature. Here in this other experiment, bottom-up, with this biphenyl 4-thiol self-assembled here in this cavity, this is a cross-section of this. We have the particle, we have the substrate, we have the self-assembled monolayer. We know now, for what I will tell you, that when you illuminate certain atoms, the metal is a little bit like a soup. This concept of having a metal rigid and the organic molecules moving a lot is kind of wrong. The metal is really like a soup. I mean, dynamical simulations, when you put a photon on top of metallic surfaces like in gold, produce this kind of effect, right? An atom that just pops up when you put the energy of a photon, right? And create this, what we call picocavity, atomic scale hotspot, right? So in these situations, Jeremy Baumber in Cambridge did this experiment on this kind of self-particle on a mirror situation. This is the Raman of such a situation, this biphenyl, and he recorded the Raman, the vibrational fingerprints of these molecules in this cavity along a couple of minutes, right? And we could distinguish 2 types of Raman vibrations. Persistent lines here all the time, and then at some point in the spectrum, these non-persistent blinking lines emerge. And these are not typical blinking lines of Raman that are moving around, like everybody who does Raman can identify. This is at cryogenic temperature, very controlled, and even with control experiments, when you turn off the light, you turn it after several seconds, you turn it on again, and it's still there. So it's a very morphological thing, right? So we associate this emergence of the new fingerprints to the creation of these hot spots illuminated by light, right? And actually this is kind of corroborated from our simulations. To explain the experimental fingerprints in this low energy region, you really need to put atomic scale hotspots close to the biphenyl in order to reproduce all these fingerprints. So really only when you assume localizations of atomic scale with certain positions with respect to the molecule is when you recover the experiment. So this is a clear hint that this atomic scale localization is going on. And in the last 2 minutes or 4 minutes, I want to close the loop and see what happens when you pay more attention to nonlinear coherent effects. It's this the third kind of methodological approach based on quantization of the fields, right? And this comes again from experimental evidence of this fantastic experiment, the same experiment. You take one fingerprint, one energy of the vibrational mode, you start increasing the incident laser power, and instead of a linear, as expected, linear tendency of the Stokes Raman signal, we identify a clear nonlinear behavior. And at that time, we didn't know either why this happened. It was very completely unknown, because in all Raman experiments, this is linear, it's with intensity, okay? So then we have to go to an optical tool, which is quantum optomechanics, because here we have vibrations, we have photons. So in optical optomechanics, the typical canonical situation is this optical cavity. Again, the 2 mirrors. One of the mirrors attached to a spring, and then when light comes in and populates the mode, we produce, because of radiation pressure, we produce this shift of the displacement of one of the mirrors, this shift of the displacement of the mirror changes the energetics of this mode. The change in the energetics of this mode produces a change in the mechanical motion, and this kind of feedback action is what people describe as optomechanics, right? The strength of this interaction, the energy of this interaction, is basically the change of energy of the cavity as a function of the displacement, and this is G0, okay? Well, the nice thing is that this canonical optomechanical system behaves exactly analog to our plasmon-enhanced Raman vibrational scattering. Right? If we put the molecule here, we might have the same situation, but the big change is that the orders of magnitude of the energy of the vibrations is completely different. In a standard macroscopic optomechanics, we have 10 kilohertz. Here, we have terahertz and faster, right? It's the vibrational mechanics. So what we are saying here is that the vibration of the molecules is modulating the plasmonic energy of the plasmon and producing a feedback here. So actually, in the landscape of optomechanics, surface-enhanced Raman scattering would play a role which is very different to all the other standard optomechanical resonators because of the losses, very large losses, but because of the very low effective mode volume, the coupling would be very close to the strong coupling, right? Let me show you in the last minute the result that we got in terms of nonlinearities. This optomechanical situation in second quantization scheme, quantum QED, it's described by means of this Hamiltonian, right? It's a standard Hamiltonian when we have this coupling, optomechanical coupling strength, the number of plasmons, the Stokes, and then the anti-Stokes. And again, this coupling strength is inversely proportional to the effective mode volume and the Raman activity. What we do now in our group is to solve this Hamiltonian by solving the master equation associated to it, plus adding all the losses of the system because the plasmon is very lossy. This requires a special treatment in quantum mechanics with Lindblad operators, etc. And when we solve that, this is what we get. We can calculate, because it's a question of population of phonons, we can calculate what the Stokes signal does as a function of incident laser power. And we can identify three regimes. A thermal regime, where the Stokes depends on the thermal phonons. A pumping regime, where the phonons start being important due to this pumping through the plasmonic cavity. And very important, this nonlinear regime, because of this optomechanical action of the plasmon. And actually, this explains this nonlinear thing. So this nonlinear evolution is basically a pumping of phonons. It's like a stimulated phonon action of the plasmonic cavity, okay? And just to finish, we did the same with the anti-Stokes. The anti-Stokes also has a quadratic behavior, which is a fingerprint of this pumping regime, this optomechanical action. And then what we did experimentally is to go again to these blinking lines that are associated with ultra small effective mode volume. And then Jeremy Baumber in Cambridge took these fingerprints, these blinking lines, and performed intensity variation here. And we saw that effectively it's corroborated that as a function of laser incidence, the anti-Stoke is quadratic, addressing this nonlinear behavior, coherent behavior of the thing. So you can see that all these effects are complex, are coherent in nature, and require this quantization of the field. So I think I have shown you what we do. Theoretically speaking, you need powerful equipment of methodologies to address plasmonics in this extreme limit of atoms and molecules, condensed matter to address the excitations at the atomic scale, the quantum chemistry to see the role of Armstrong scale distribution in non-homogeneous fields, and then to address nonlinear and coherent effects, cavity QED. So you need to do a few things, right? Let me acknowledge the people, of course. I lead a group of very nice people, Ruben Esteban particularly, Nikolai Schmidt, Zhao Zhang, Thomas Newman, and Mathieu Urbieta. And then the collaborators, Daniel Sanchez Portal, Andrei Borisov in Paris, Alejandro González Tudela in quantum optics in Garchim, Francisco García Vidal in Autonoma, and then the two key experimental groups that we have been working for several years, Shen Chaodong in China and Jeremy Baumber in Cambridge. And with that, I thank you for your attention.